Oh. Okay, that one. Okay. I mean, there's been a lot of. All right, that was it. Oh, that's my way of saying hi. Hi, hello. You know what? I'm gonna sidestep the whole madness for a minute. I'm just gonna say hi to Lizzie and May. How about that? And Jayla. How about that? And Eric and Newell. How about that? I'm just saying. I'm just saying. Wait, no, I'm not really, but I am saying hi, John. Hi, Maisha. Hi, I will. John, I think John has stepped back into the ring. That's all I'm saying. But no, hi, John. Hi, Maisha. Hi, Jayla. Hi, hi Maisha. Hello, Eric. Hi, oh boy, you see, there they go. There they go. Okay. Whoa, yowza. Okay. Hi, and good afternoon, New Elsie. She gives me two highs. That's all I'm saying. Hi, oh, and then he says hello to her. Okay. And hi, and good afternoon to Lizzie. And notice she says hi to everyone. See, she's about the group, right? As is May. I mean, and May, see, May is about so many eyes. May has so many eyes that she's a we. You know what I'm saying? We, you know what I'm saying? Okay, I don't know what I'm saying either. But so yes, hello Lizzie, hello May, hello. Now Noelle brings it back around, and then Maisha. Okay, it all gets complicated. Oh, and then May and Maisha and all that. All right, and then a Lizzie, and it comes all around. I can't even keep up with you people. Hello. Oh, and finally I get a hello from John. Okay, thank you. Lizzie is great. Yes, Lizzie is great. I mean, that's not even the question. I mean, and notice that Jayla just lets the madness go, and she just quietly takes her throne in the queendom of serenity, as does, but did I say that Jayla's doing that or Noelle's doing that? They're both doing. And then May has a lot of exclamation points. Okay, no, I love this whole class. Have I mentioned? Hello, everybody. Who was on? Wait, and Eric, hello, Eric. Okay, I'm going to go around. And Lizzie does have video too. Can we just point that out? But Jayla and May and John and Maisha have avatars. So let's point that out. So I have to say hello, Eric and Noel. Okay. Didn't finish. Oh yeah. Okay. No, that's good actually, Maisha, about the homework too, which we're going to get to. Oh, and John. See, even Maisha and John can be friends when it comes to the difficulty of homework too. Oh, and then Lizzie thanked her. Okay, I'm going to stop getting sucked into the chat. But yes, no, we are going to deal with homework 2 today. Let me say, like, hello. Yes, we're homework 2 is the agenda item for today. Hang on one second, actually. Sorry. Homework 2 is the agenda item for today. Oh, okay, I can't. Sorry, I want to do. All right. We're going to get to homework 2, like essentially now. Oh, yes, it is. Well, happy Pi Day. It is March 14th, right? 314. It is Pi Day. Is that, I mean, let me be the 90th today to remind you of that. If I could bake and we were not in virtual reality, I would totally bake you. Oh my God. Okay, the madness continues. But please notice also it's Pi Day. That's a contrivance. I mean, it's not like Archimedes called it Pi Day. It's not like Archimedes was on the same calendar, but it is like Albert Einstein was born today. Just saying. I'm just saying that Pi Day 314 Day does happen to be Albert Einstein's birthday. I'm just saying. Also, I'm just saying that, you know, Galileo died in like March or some month of the year 1642 AD. On Christmas of 1642, Newton was born. Now I'm just saying. I mean, is that a coincidence? I don't know. Is that odd or is that God? I don't know. I'm just saying. But okay. Oh yeah. Oh, Maisha said. I mean, wait. I'm totally looking at the chat now. Hold on. But you know, yes, Lizzie, you should totally bake pies. And yes, right. I actually think there are no coincidences in physics. In fact, Professor Wu once said that to me many years ago. He once did say, you know, I think that the point of physics is that there are no coincidences. I think he's onto something there. I also think I'll say this many years ago. In fact, I'll tell you what year, the year 1994, I had a physics student that I'm still friends with to this day. Obviously, I mean, she's like a person now. Like she has she's 3 children. One of them is in high school and doing badly, and it's like traumatizing her that her child is doing badly. But she wrote me a letter about the very first time she got a 62 on a physics test in my class. I mean, this is what she was. This is back when I was a high school teacher. She was in high school, but at the time, and she to this day, she's still upset about the 62 she got on her first physics exam with me when she was in AP physics in high school. I didn't know this. Now I feel guilty that she's still carrying this around. But she got a 62 on this test, and she's telling me, this is literally, I mean, I shouldn't be said, but I'm not mentioning any names. She's literally telling me on the phone just last week. I'm talking last week. This person like has 3 children. She's like in her 40s. And she's telling me last week on the phone about how this 62 on a physics exam in high school, AP physics, like upset her so much. And she says, and I can't, it was so upsetting when I saw that 62 in your handwriting and that F in your handwriting. Like, I didn't even know if I could look you in the eye again. And I said, hang on. You might have seen a 62 in my handwriting. Like, I didn't remember, this was a long time ago. I didn't remember. I said, but I guarantee you did not see an F in my handwriting. And she goes, what do you mean? I got a 62. It's totally a failing grade. And I said, it may or may not be a failing grade. Like, maybe it is a failing grade. Maybe it is a failing grade. I said, but I know this, even in my first few years teaching, I knew better than to ever write an F on someone's exam. That you might say that you failed. You might think that you failed. That's up to you. I'm not saying, I mean, getting 62% out of getting 62 things right out of 100, depending on how hard they are, that I don't know if that's failing. To this day, I don't know if that's a failure, especially if it's your first time taking physics. And I don't know if it means you're going to get an F on your report card. I just know, oh, this is very weird too, I'll tell you. Okay, anyway, I just know, I was just saying you got 62 out of 100 correct on this exam, and which does mean you got 38 wrong, I mean, out of 100, but I guarantee I did not write F on your exam. I would never do that. Like, that is not my evaluation to make. And she goes, yeah, you totally did. You totally did. I said, no, I didn't. She said, look, I failed. I failed. We can admit this to this day. I failed that exam. You gave me an F on that exam. And I'm telling you, this is last week. This is someone, I mean, who took an exam. I mean, she took the exam in like 1994. And last week, she's still talking about this. It's a friend of mine. Like, I'm not making fun of her. Like, I'm sympathetic. And I said to her, there's no way. There's no way that I actually wrote the letter F on that exam, even if I don't remember the incident. I just know, and even if I've changed as a teacher, I know I wouldn't do that. She found the exam, people. She found, and this is how crazy, she found the exam, took a picture of it, texted me a picture of it. I mean, again, this is someone in her 40s who has this exam still. That's how upsetting it was, like her first failure ever. Right. And by the way, she's also a radiologist. I mean, she's like a medical doctor, like with the degrees up the yin yang. I mean, and she has a swimming pool. I mean, she's quite successful in life. But this F that she got once in high school, she's still carrying around. I mean, mentally. And she showed me a picture of the thing. And guess what? I'm just saying to everybody, guess what? There was a 62 on that exam. There was no F. And she admitted it. She's like, you were right. You were right. I was wrong. I've been carrying this around my whole life. But you're right, it doesn't say F anywhere on this exam. And it was very good of her. I mean, and the point of the story is not like, and I was right and she was right. The point of the story is like, we can turn these things in our minds like, whoa, like it literally, I mean, she had the exam in her possession, but she had never looked at it closely enough to notice it didn't say that she was a failure. It didn't say that it just said you got 62% correct out of 100, all judgments. And I'm saying this to you guys now too. This is a very successful person in her life, super successful, still takes grades very seriously, takes the grades of her children very seriously. I take the grades of my children seriously. I take your grades seriously, but let's not let these things define our sense of self. Please. I mean, this is not about cosmic success and cosmic failure. This is about how many right and how many wrong on a test. Anyway, whatever. I'm going to look in the chat, but that is a true story that just happened, and I shouldn't be talking about it, but I am, because it just happened. But what the other weird reason I think I'm talking about it, this is the other weird thing, is that it is, oh yeah, it's Pi Day, it's Albert Einstein's birthday, right? Is that a coincidence? I don't know. But the other non-coincidence is my physics mentor, the person who taught me how to teach physics, the person that I was teaching with back then in 1992, with whom I'm also friends to this day, he and his wife is the one who taught me how to appreciate art. Now, I'm still terrible at art, but I didn't even appreciate it until I took lessons, like lectures from her, and now started to at least understand how to look at paintings and appreciate them. Whatever, those two people are like my mentors. They're still friends with me to this day. They had a son named Elijah, who was born in Albert Einstein Medical Center in Sao Paulo, Brazil, roughly 20 years ago today, i.e. my physics mentor's son was born in Albert Einstein Medical Center in Sao Paulo, Brazil, on Albert Einstein's birthday, Pi Day, about 20 years ago today. So this is a shout out to him. Happy birthday, Elijah. If you're listening, and that's ridiculous, why would like the son of my former physics mentor be listening to this freaking YouTube that is about your class? But the answer is he used to actually watch them all the time, and I have no idea why. So just in case he is, shout out to him. Happy birthday. Okay. Now we're going to go over some homework, but first I'm going to look in the chat. Okay. Okay. So yes, happy Pi Day is really the lesson of all this. It is Pi Day. By the way, notice you notice how theta, like pi is just the circumference to diameter ratio, right? That's all pi is. It's like if you hacked across a tree, if you just hacked across a tree of any size and like put a piece of string along that hack, along the diameter, and laid the string down on the ground, and then you took another string and just wrapped it around the tree and laid that down on the ground, right? You just compared the two pieces of string, like going across a tree versus going around a tree. If you just compared the two, it turns out that one string would be a little bit more than 3 times as long as the other string. Always, no matter how big the tree is, right? That's what pi is. It's that ratio of going around to going across. Now, is it a coincidence that theta, the symbol theta, which is the symbol we use for angles, is just a round circle with a cut across? I don't know. Coincidence? Is that odd or is that God? I don't know. Is that work or is that a quark? I don't know. But I'll also tell you this. If one thing that theta is meant to connote that I hope everybody, if nothing else, takes away from this class, an angle is just a portion, a fraction of a circle. An angle is a fraction of a circle. Irregardless, irrespective, independent of how big that circle is, right? When we say pi radians, we mean halfway across the circle, no matter how big the circle is. We say pi over 2 radians, we mean a quarter of the way across the circle. When we say 2 pi radians, we mean 1 full circle, which in this class means 1 full cycle. A radian, 1 radian is just a 1/6 of a cycle in this class from here on in. That is the connection between Pi Day and physics today that we're going to get going over that homework in a moment. But first, I'm going to finish reading the chat because that's what we do. Okay, hold on. A tiny pie maker. Yes, Lizzie, please. And Lizzie, now she's obligated. She's got to start making pie now because Lizzie, I do run into in physical person sometimes. So now, like, I'm going to expect next time I see her, like on the steps of John Day on a Tuesday, I'm going to totally expect a piece of pie. Thank you, Lizzie. I totally appreciate it. Okay. I look like all of them combined. That's hilarious. Oh, I look like oh yes, I look like Galileo and Newton. Yeah, I guess that's probably true. And that is not a coincidence. You got to try to look like your heroes, right? I thought you meant I look like all my former students combined, which is weird. Oh, good afternoon, Alea. It is great to see you. Sorry for my delayed good afternoon. I know you've been here for hours. Sorry. Oh, Maisha looks like, oh, okay. Whoa. Now it's getting a little dicey in the chat here. The chat is getting a little, whoo. I'm trying my old white man privilege. Oh my God, I don't even know how to deal. This is why luckily, okay, happy Pi Day. Yes, happy Pi Day, Noel, awesome. And he was talking about the president. Okay. Yeah, oh, now it's getting dicey again. Oh my God, I can't handle the heat. I better get out of the kitchen. Oh, which reminds me of pie. Yes, Elizabeth, thank you. Yes, happy Pi Day to you, Elizabeth with an S. Okay, what? Oh yeah, all right. And then Maisha's talking about the homework. Wait. Oh yeah, she sounds like me. Yes, well, there's a little F in the chat. That's hilarious. Emotional damage. Oh, nice little, I like those stars, JLO. That's cool around the emotional damage. I've never enjoyed emotional damage so much as when JLO just wrote it in the chat. Okay, F to pay respect. Also, it was just, oh, good point, John, that it was 3:14 o'clock. Sorry, I totally missed that 6 minutes ago. I've been talking for I've been talking for 15 minutes and haven't said a god darn thing. Lordy. Okay. Yes, yes, gifted kids. Burnout. Well, that's interesting. I don't even want to. The thing Maisha is saying about burnout and gifted kids, like I don't. That's like almost too serious for me to want to deal with. But oh, that's so sweet, Jayla. Thank you. I'm not even gonna. I can't even make a. Thank you. With educators, that's nice. Okay, I can't even. I'm like, okay. Oh, thank you, Maisha. The funny is, I'll tell you one thing. No, it's nice of you to think, all right, well, Illuminati. Okay, and I'm going to go, but one thing is, you've met my children, or at least one of them, and I'm not going to say, I'm not going to go there. All right, I'm going to go on. Okay, Lizzie being proud aloud, that's hilarious. Okay, pie physics, it's like a tiny pie maker. Yeah, it's like a Holly Hobby pie maker, no doubt. Okay, is that what they call it? Holly Hobby? All right, whatever. I say, yeah, I do know, I am kind of sporting the Dumbledore thing. I can't deny it. I don't know. I mean, I could do worse, I suppose. I do sort of, but anyway, all right. Yes, yeah, Lizzie is definitely now on the, I can't believe I'm dwelling in the chat here. I know I've got to get to physics, but all right, pecan. Okay, now it's getting crazy. Okay, so easy bake. That's the word I was looking for. Thank you, Elizabeth, with an S. Yes, easy bake. That's hilarious. I totally get that, which is sad. I'm actually amazed they still have those in life. Pokemon. Okay. Now you guys are doing that thing where you're just going to keep the chat going. Oh no, you're not. Okay, great. You try. The world's good. Okay. It's like some weird tiny pie maker from Bed Bath and Beyond. Okay, that's hilarious. Okay, no, I'm not going to go there. That's hilarious. I feel like from now on in all this calculus we're doing, we should like totally just substitute the word beyond for the word infinity and be like, the limit as x approaches beyond is y over Bed and Bath. Okay, but no. All right, that's stupid. Yes. All right, let's get to all right, we're gonna get to physics and we're gonna get to like homework 2. Let me quit. Okay, I have to be careful. Let me say to all of you, like technically homework 2 was due today. But a couple of things about that. Number one, you may or may not have noticed, I still have not given you back homework number 1. That does not mean you should not do homework 2. If you want to know what's going on in class and like be invested and care about class, it's good to do the homework for sure. But that's funny. Oh my God. Okay, that's funny. But look, when it comes to the homework, as opposed to exams, and also strangely, as opposed to the game homework, but when it comes to the actual homework, the idea is just to stay ahead of me. The idea is to have attempted the homework before I start going over it, because the idea is you will eat better. There's a metaphor. You'll eat better if you're a little bit hungry, right? You'll get more out of class if you come to class with concerns or questions or curiosities that I can then use class to address, i.e. if class is a little bit more like recitation rather than just some like blank PowerPoint that's like happening in Nowheresville, right? So indeed, I assign these homeworks and then you come to class. It is ideal if you do them, if you attempt them before class, ideal. And in fact, I would like to give a shout out to those people who have actually already handed in the homework, but I can't because if I switch it, well, maybe I can actually. I will in a minute, but let's make this clear. Yes, if you've already attempted the homework in some way and handed something, then that is great. And I may want to give a shout out to you literally in a moment for doing so. But just because there will be praise unto ye who have done the homework before today, that does not mean that those of you who have not done it are to be damned. And I'm darn serious about that distinction. And I hope you believe me at this point in the semester or 2 semesters, that I'd like the people that do the extra or do the thing or do the right thing or do the good thing to feel that reward and that benefit and that praise. And I'd like it to be recognized. But at the same time, I'm not interested in punishing or condemning or shaming anybody who, for whatever reason, is doing things on their own pace. What I'm really literally trying to say to all of you is, first of all, if you did hand in that homework already, but Google Classroom says you're late, don't worry about it for 2 seconds. Second of all, if you haven't handed in second of all, if you attempted homework 2 in any way and handed in anything, that is great. And if you didn't do that last section on vectors, that's totally fine. I think I even explicitly said in advance, the last section on vectors is ultimately necessary, but not necessary for right now. So if you did a bunch of it and you didn't get to the vectors thing, you can do that later, no problem, and no penalty and all of that. Third of all, if you haven't started yet for whatever reason, okay, you might not get as much out of class today as those people who did start. I mean, that's the reality. That's called a literal consequence, not a punishment. But nonetheless, I'm going to start going over it today in class. And if you didn't start it yet, you can absolutely use what I say in class today as a helpful jump start for you to break through whatever psychological wall and attempt it. And, if I say things in class today that help you get over that wall, good. We all know I'm not going to finish going over it today, especially at this pace of talking about things. I'm not going to finish going over it today. If I can help you start it, then start it and hand it in. And the people who already handed in should feel rewarded and wonderful. And the people who have not should not feel punished. It's just that straightforward. If you use today to correct things that you already turned in, but you were wrong about, whatever, good also. Leave the old draft so I could see how hard you're working and upload a new draft. Like really, really, really. What I'm really saying is you hand in the homework when you hand in the homework. And if it's a little bit later than I said, or if it gets revised as we're going, don't worry about point penalties. They won't, that's not an issue. It's going to take me a while to go over this homework. Your goal is just to always have thought about something before I start raising it in class. That will help you do better on the exams. Finally, on that, the exams, I don't like to be late. When we get to an exam, which is sort of soon-ish, we start talking about it, I will say there, you're going to have to turn it in on time. Like that's different. That's an exam. Also, the game turns, I do like you to please turn on time because I think they're really quick. I don't think they take much. And if you turn in a game turn a day late, you still get a lot of points. It's just you get 4 points instead of 5. That's all. But on the homework, even if it's late, you're still going to get all the points. And your goal is to eventually get all the points, even after as many revisions or delays as it requires. Okay. So we're going to go over we're going to start going over homework 2. We are going to start going over homework 2, like right about now. If you want to use this to correct something you've done, fine. If you haven't started it yet, fine. Oh, but I will. But having said all that, one last thing. Okay, sorry. Having said all that, bear with me for a second. Sorry. Bear with me for a second. Or bear with me for many seconds. So you are this class coming. I'm not here. I'm sorry. I promise I contracted ADHD before it was ever invented. So that's a defense. Cameron is actually, it's not computer. Sorry. Okay. So I'm just here to say, okay, again, now this is the fine line that I choose to walk. For whatever it's worth, I'm here to say, shout out to Maisha, to Noel, to Elizabeth with an S, and to Stephanie, just acknowledging they totally did turn in the homework like before today. Thank you for doing that. I'm not looking at any other names. I'm not saying anything about anybody who didn't. Like, you'll still turn it in. It's all good. No one's losing any points or anything like that. But yes, just an acknowledgement and a shout out. Thank you, Maisha, Noel, and Elizabeth, and Stephanie for contorting your lives to make it possible to get this thing in today. Again, fine line. I'm saying praise be unto you for that's awesome. I'm saying no shame, no condemnation, no punishment to anybody else. And I don't know anybody else's name as I'm saying that. I'm not looking at anything negative. I'm just acknowledging a positive. That is a fine line. Take it or leave it. Now, but again, for anybody who just tuned in, and there's 2 people coming in. Again, I'm saying if I just named your name, that was not to embarrass you. That was to thank you. If I didn't just name your name, it just means get in the homework when you can, and you're not losing points or anything like that. Okay. So now I'm going to start talking about it, and it may help some of you get off the ground. Oh, I have a question. Okay, question to do. Wait, I have to do. Okay. Wait, this is perfect. Okay, I'm about to literally now, with all my yammering aside, we are literally going to get to homework 2 right now. And again, I'm saying we're going to start going over it for everybody in the room, whether you've done it or not. I do hope that whether you've done it or not, you sort of have the questions in front of you. Like that would be helpful. I'm about to start going over them. I don't care. I mean, yeah, like I think you can get something out of this, whether you've attempted it or not. But interestingly, in the chat, there's a very good question about the actual homework that I totally want to address. I mean, it's Maisha's question. It's a public question. Maisha's question that says, after doing the derivatives, it asks if the given equation is a solution to the differential equation. What does solution mean in this context? That is a great question. I am going to answer that maybe in too much depth when we get there. But my fast answer right now is a solution means, does it fit? Does it satisfy? Is it consistent with the differential equation? Again, I'm going to be more detailed than that in a minute, but for something to be a solution to a differential equation means it's a function which, when you take its derivatives, do you find what the differential equation says that you should find for its derivatives? So that's a very important question, and I'm going to answer it more when we get there in the homework, but yeah, that's it. And then what Maisha just wrote, right, it means that it could be rewritten like into the differential. Yeah, to be, all right, I'm going to say this in general, and then we're about, well, hold on, let me, 1 second. Okay, so we're about to start going over this homework 2. A differential equation, remember, a differential equation necessarily, by definition, relates some kind of derivative to a dependent variable. A differential equation of any kind will say that like dy dx, for example, dy dx is equal to some kind of function of y. Like that would be an example of like, this is not our differential equation here, but an example of a differential equation might be dy dx equals 5y. That would be a differential equation. And what a solution to it would be is some expression that presents y as a function of x. A solution to a differential equation is a expression that relates dependent variable as function of independent variable. And that's a standard function, like y equals blah, 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 x, or x equals blah, 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 t, or z equals blah, 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 y. A solution should look like a regular function mapping a dependent variable to some independent variable, as opposed to the original differential equation itself, which always maps some kind of derivative to some kind of dependent variable. Like a differential equation is like backwards. It says that something is a function of a dependent variable rather than an independent variable. And then you have to unpack the differential equation to get a regular everyday function dependent variable of independent variable. So for something to be a solution to a differential equation means it's a function that fits, that satisfies, or that, as Maisha said, or could be rewritten into the differential equation. Like, so that's right. I mean, I think Maisha's wording is fine. But differential equations, the thing to everybody is that a differential equation really, it's an equation, so it like looks like an answer. It looks like a statement to us. It looks like the end of some math road, but it's really a question. A differential equation needs to be solved. A differential equation relates a derivative to a dependent variable. And what we want to solve it is a dependent variable related to an independent variable. When we find one that works, when we find a dependent variable as a function of independent variable that actually is consistent with that differential equation, then we say we have found a solution. We have found something that solves the differential equation. Okay, so I'm going to get specific now in the homework, like, but that is a very important question. That is what we're like trying to deal with here in the math that underlies the physics. All right, so let me just switch gears here. Okay. So we're on homework number 2, math methods, Roman numeral 1, derivatives. And the given is x equals a cosine omega t. Now, please note, like on this screen here, what I'm doing at first with 45 minutes left, at first I'm going to walk us through this homework in the ideal optimum solution kind of way. Like I'm going to include all the steps that I would sort of hope or ask you to include when you're turning the homework into me, or when you're turning an exam into me. Like I'm literally going to remind you, like in the margin here, step 1, diagram and fact pattern, et cetera, et cetera. And I'm trying to show you here that even these little practice exercisey, these little math practice exercises, even they can and should be broken up into the 5-step method. Even if you think you can do some of these questions in your head, which I believe some of you can, even if you believe you nearly instantaneously see the answer to these questions in your head, what I'm here to urge, so even if you think they're easy, in other words, that's great. All the more reason to use this as an opportunity to break down your thought process, to slow down your mental movie, and express all the steps that your mind went through super quickly to get you to that answer. And what I'm trying to say is, even when you think you can see the answer right away in your mind, that's just because you are that smart and that good and that fast. It means your mind still rapidly went through a whole number of steps to get to that answer. And it is best for all of us if you actually investigate and express those steps, if for no other reason, so that you have steps to look at for whenever you finally arrive at a question that you cannot solve seemingly instantaneously. Okay, so even for this first question, the given was x equals a cosine omega t, and I made a little diagram for it. There was no diagram in the question. I made a diagram. All the more reason to make a diagram that one wasn't presented. So I made a little diagram of a cosine function, and notice this. I made a function, a cosine shape, where x was being measured as the dependent variable, t was being measured as the independent variable. And notice that even the a and the omega those details are even made clear in my little sketch. Like a is the amplitude, or of that function, or put another way, it's the value of x when t equals 0, right? That's what a is in that function. It's the same as x naught. It's the value of x when t equals 0. So I labeled it on my axis. And where's omega, like in that picture? Omega is literally, omega is 2 pi over the period. Omega is the angular frequency, the number of radians per cycle. Excuse me, sorry. It's the number of radians per second, per unit of time, per unit of advancement on the independent axis. So omega is 2 pi over t. Therefore, t is 2 pi over omega. T is 1 full cycle from crest to crest, or from trough to trough, or whatever you want to call it. So that's there in my picture. Omega is 2 pi over the period. Okay, so that's my givens. And then step 2, what's the question? The question is find dx dt. Okay, now again, hopefully if some of you were sort of paying attention last week, or you remember this from calculus 3 years ago or whatever, like for some of you, you might do it in one step. Sorry, you might do it really fast in your head. But some of you are still refreshing yourself on the calculus. And no matter who you are, even if you're really fast at calculus, please notice that there are some things you had to know about calculus in order to get this derivative, right? I mean, question 1 is just asking what's dx dt? What is the derivative of that x function with respect to t? We are treating t as the independent variable. We're treating x as the dependent variable. We're asking what is dx dt? And I'll tell you in step 3, general definitions and principles, well, one thing I'm just writing in English, I'm saying that expression x equals a cosine omega t, that is a trigonometric function of a function, right? It's a trigonometric function of a function. It's cosine of omega times t. It's not cosine of t, it's cosine of omega times t. So I'm just writing in English here. We're going to need like to know our trig derivatives, and we're going to know chain. We're going to need to know chain rule to do this. You don't have to write things exactly the way I am, but put another way to write it, excuse me, more mathematically. So I'm still in step 3 here. And by the way, also I know some of you might not have written out this much. If you didn't, I'm not saying you have to redo your homework, but I'm telling you, this is the optimum sort of level of response here, especially if you're trying to practice and know these things. I'm also telling you, I'm not going to write this much for the rest of the whole homework. If you're already wondering like, oh my God, we're going to be here forever. I'm not going to do this every time for every exercise in the homework, but I'm just showing you now in the first exercise, what would be an ideal optimum response. So I'm still in step 3 here, general definitions and principles of this exercise. General principle number 1 is if y equals cosine of x, then dy dx equals negative sine of x, right? I mean, the brown part. I know it gets a little sloppy with the black, or put another way, it says in black next to it. If y equals a cosine of x, then dy dx equals negative a sine of x. What I'm trying to say here, now you might, okay, so I'm talking about physics and math now, right? Like all joking aside now, you might be looking at this, the top of the sheet and going, whoa, wait, what's like, even if you got it right, you might be thinking, what is he doing? Like, besides that, he's making it much more complicated than I thought. Like, I thought I got this right. Can we move on? And I understand you might be thinking that, but you also might be thinking, wait, where's he getting y's and x's? We had x and t here. Good observation. If you're thinking that at all, good observation. What I'm saying is, I'm switching to y's and x for a moment, just to make a larger mathematical general point. I'm saying in general, like in a math class, if you just had y equals cosine of x, then dy dx equals negative sine of x. That's just my mathematical way of saying, like in general, the derivative of cosine is negative sine, right? Like that is a step. That is a step. You might not have written it down. Don't regret it if you didn't. But I am saying, let's get it straight. I don't care how smart we are or how fast we are. We had to know that in our mind in order to do this derivative, right? You have to know that the derivative of sine the derivative of cosine in general is negative sine. Going one step further, actually, you'd have to know that the derivative of a cosine, like capital A times cosine, equals negative a times sine. Like that's a step in the reasoning. It's worth writing down. Then, right? So I'm in that YX land right now because I'm making a general, this is like when you write like a, if you just had a straight up physics exercise and I said like, F is 12 newtons, M is 3 kilograms, what's A? You would first write F net equals MA before you write the general concept you would write down, then you would plug in. So that's what I'm doing here. The general concept is, in general, if y equals cosine of x, then dy dx equals negative sine of x. Then I'm saying underneath that, so I'm like on the third line of the sheet here, then I write if y equals f of x. So in general, this is a math point. If y is some function of x, if y is a dependent variable and x is an independent variable, and let's say, and if, like, so I'm in the brown, I'm in like the third line of brown here on the sheet. And if in general, z is some other function of y, okay? So I'm being general, but I'm being specific. I mean, I'm being general, but I'm being deliberate here. Imagine that y is some function of x, like you plug in some x, you input some x into a box, out comes an output called y. Then imagine you take that y and you put it in a different box called the g function, and out comes z, right? So I'm saying, imagine if you have a function of a function. You got some x value, you put into a box called f, out comes y. Then that y goes into a box called g, and out comes z, right? Imagine if we have a function of a function. Then, according to math, according to calculus, and according to a notation that I think makes it somewhat sensible looking, then the derivative of z with respect to x, dz dx, right? The derivative of the whole mishpucha, like of the whole thing, dz dx equals dz dy times dy dx, the derivative of the outer times the derivative of the inner. That's what that says. That's called chain rule, right? Honestly, and that's not a proof of chain rule. I'm just saying that's the chain rule. It's not a proof, but I will say this. When you write it like that, it kind of seems like it makes sense, doesn't it? Like I just memorize. I mean, chain rule to me was like this garbage. Like, okay, if I have a function of a function, then I multiply by the inner function. All right, fine. I multiply by the inner function. I don't know. But it kind of makes sense when you think of it that way. If you want a function of the whole thing, it's a function, it's the derivative of the outer multiplied by the derivative of the inner. And like the middle part sort of cancels out like that. So that's the chain rule. And that's what's happening here, right? Because we have t. So here it's not z. So I'm just reminding you of chain rule. I'm just saying there's no way you get the derivative of a cosine omega t. Like you might now sort of have memorized it from last week, maybe, but don't. Like it's based on reasoning. And even if you can do the reasoning really fast, you have to have the reasoning in your mind to do it. I'm saying we're doing a trig derivative and we're doing chain rule. And I'm saying here the chain rule is happening because we're plugging t into a box and the box says multiply by omega. And then that comes out, omega t. And then we're plugging that into a cosine box and out comes something, right? That's what we have here, a function of a function. So putting those two things together, now I'm in step 4. So I'm in the middle of the page now. And again, I'm dragging this out. I'm not going to drag every single one of the homework exercises out, I promise. But this would be an opportunity for you to stop me if any of this doesn't make sense. Again, do you literally have to write every little bit that I wrote down? Maybe not, but I hope, but try and definitely see if you understand everything I'm saying. I'm saying now in step 4, my particular application and work, I'm now applying the chain rule and the trigonometric derivative. So I'm saying thus, if y equals a cosine omega t, then dy dt, right? So it's really kind of like y equals a function of x and x equals a function of t, right? Then dy dt equals negative a omega sine of omega t. Like really it's negative a sine omega t and all multiplied by omega. So then I brought the omega out, like maybe I skipped a step there. And that's my answer for the very first question on homework 2. My answer to the very first question is if, so I should even probably say, well, I'll say, hold on a second. So if y equals a cosine omega t, then dy dt equals negative a omega sine omega t. You could say if this, so some of you, I mean, really, I'm saying this, I'm saying, right, I'm saying negative a sine omega t times omega, but then I'm just saying multiplicate, I'm just collecting the two constants omega and a and putting them together. But that's a parentheses. So I'm going to go to the next question 6. So all we just took a derivative. It was just a math question, but of course we're on purpose taking a derivative of cosine function because we're looking at the cosine function for physical reasons. One last thing, again, just in terms of what, like, everybody does the homework slightly differently. The more steps you include, the more it makes it your personal homework, that the more I know that you actually understand it, you're not just copying. But just say you're in the middle of exam or homework, but if ever you have a moment where you're like, oh, I could put in this extra step, but does he really want me to go that level? Like, should I actually write down chain rule? Should I actually write down that derivative of sine is cosine? Like, if ever you ask that question of yourself, the answer is yes. If you can envision an extra little step that you could put in, if you can envision breaking down your reasoning even into a smaller level, the minute you even see that smaller level at all, if you can ask the question, should I include the step? The answer is yes. I mean, better safe than sorry. The more, the merrier. Like the more we can break this down, the better. The worst cost is that you took 30 seconds extra to do your homework. But like the dividends are infinite and beyond. They're like beds and baths, the dividends, really. Okay, so that's the answer to the first question. Now we're going to start speeding up a little. Stop me if you don't understand, but that's just a math question. What if the function is the a cosine omega t. What's the derivative? The answer is negative a omega sine omega t. Now we go to the next question. So the next question is, what's the second derivative? Okay, I'm still sort of being a little bit long-winded here. What's the second derivative? Notice for step 3, I just want you to notice this. For step 3, I write down as a general definition or principle, I write down in the second line, you're right, d2x dt squared by definition, triple equal sign equals ddt of dx dt. Now, why am I bothering to write that? Now, and I pretty much expect, even the 4 of you who did this homework or whatever, I don't expect that you probably wrote that down. That's a little bit like me talking, but it wouldn't be a bad thing to write down. But I'm not saying you necessarily wrote that down. But look at that for a second. That's actually kind of an insight. First of all, what I'm saying there in English, in my little step 3 GDP here, I'm saying that the second derivative of x with respect to t, by definition, equals the derivative of the first derivative of x. First of all, that's what I'm saying. I'm saying, like, in order to get this next question, all I have to do is take the derivative of my answer from the last question. First of all, that's already kind of an insight. My brain had to, for me to go on and answer this question, my brain actually did have to realize that. Whether it realized that it realized it or not, my brain does kind of have to know that a second derivative is a derivative of a first derivative. So I'm writing it down. I'm never going to write it again, but I'm writing it down once now to be sure. But also, please note, look at that notation. Look at that freaking notation. d2x dt squared equals ddt of dx dt. Now look, that actually says, like, I will tell you, if you're anything like me, and God, I hope you're not, but if you're anything like me and you forget to shave for like 2 years of COVID, you might have the problem that I did in early calculus, where they always wrote second derivative as d2x dt squared or something, right? Or d2y dx squared. And that totally bothered me until it stopped bothering me because I just accepted it. And that was even worse. In other words, I was always like, why are they so freaking inconsistent? Why are they right? d2y dx2? Like, and really what my brain did, and I'm not kidding about this, my brain at first was like, huh? Like it bumped. Like, why is the 2 in the top, in the middle, but in the bottom, it's like all the way to the right? Like my brain first was like, huh? That looks weird. That looks inconsistent. Is that a mistake? And then I found out it wasn't a mistake. So I was like, that's weird. So then what did my brain do next? My brain was like, all right, I guess I have to accept it. It's another one of those stupid math things. My brain did. It was like, all right, this is another one of those dumb math things that they just do that just doesn't make any sense. And it's not meant to make any sense. And it's totally self-inconsistent. And I guess it's just another one of those things in math where either they're doing it to give me a hard time or to make my life more difficult, or even if they're not on purpose making my life more difficult, they just don't care how difficult my life is. They're just willing to make no sense because math just makes no sense. And it's just my job to just accept it. So I just accepted it. And what happened is I went on and then continued for a number of other examples like that to just believe more and more that math was just something that I just had to accept and do whatever the teacher said. And it wasn't really about sense or reasoning or anything that was natural. It was just like crazy garbage, right? Now, I'm not saying that any of you is literally consciously sitting there and saying that, but you might be, and you might have. I'm here to tell you, no, actually, that's not the deal. Sometimes math moves way too fast for us, so it looks like it makes no sense. But the truth is, if we slow math down and break it down into lots of little steps, it turns out there's a huge amount of thought and care and sense that's going on even in these simple notations. The reason D2, and the more we believe that, the more we might slow our own math down and really if you can assume that everything in math actually does make sense and that sometimes we don't get it right away, but that if we think about it enough, it actually will make sense. And when I say it actually does make sense, I don't just mean to some other crazy dead genius who died in 1642. I mean, it makes sense, like to us, if we slow it down and look at it carefully enough with enough faith. I'm saying that the reason second derivatives are written as like d2x dt squared is because look in the second line of my sheet. The second time derivative of x really is the ddt of dx dt. What we're trying, and if you write it like that, you'll see why it's like d2x over dt 2. What we're saying is that it's an operation being performed on an operation, that the second derivative is do this thing to a function with respect to time, and then do it with respect to time again. What it's not is multiplication. If we wrote second derivatives as dx2 over dt2, which is what I wanted and which is what I initially thought would make more sense, and initially it does look like it would make more sense to write dx2 over dt2, that looks like it would make more sense, but that would actually mean dx dt squared. That would mean take a derivative and then multiply it by itself. That's not what we're doing. We're doing an operation twice. We're not multiplying. It actually makes sense to write the derivative, the second derivative, the way we do. Now, that's just a minor public service announcement. That's just a minor digression. That's not a digression about how this notation actually means stuff. And it doesn't always mean stuff immediately to us. But the more we can believe that it actually means stuff, the easier it actually is to do math in the long run. Assume that it actually does make sense and look for the sense in it. Don't give up and just be like, oh, yeah, it's just freaking black magic. I'll just do whatever. Then you won't advance in math because it actually isn't just black magic. Okay, anyway, whatever. So I wrote, oh, thank you. That's so, I love this. That is so nice of you. You totally submit that for points, by the way. I like the like. I appreciate it. Like whatever that caret symbol is. Thank you for saying so. And I appreciate. Anyway, I appreciate. I won't get all stuttery, but I will. But thank you. Well, my work here is done. No, okay, cool. No, I appreciate it. And please do submit those for points, not just because you're making me feel good, but basically just because you are making me feel okay. So but also that does show she's paying attention, right? I mean, like that's like a double dip right there. I mean, obviously. All right. Anyway, so then the next so therefore that justifies I'm now going to take the derivative. Oh, and funny, now because Elizabeth with an S just did that, it actually makes me realize that I actually had a little mistake there. Sorry, that should be DDT. After me yelling and yelling and yelling, I should. All right, so now I'm going to take the derivative with respect to time of the derivative that I already took of the answer I got in part A. So I'm taking the derivative with respect to time of negative a omega sine omega t. So now here again, and you could write this or not, like, you know, again, or okay, I'll even say C above for chain rule and trig. Oh, and I suppose now that I think about it, technically here, what I could put in a step 3, I'm just not going to crowd this page. I could put in a step 3 that now, you know, if y equals sine of x, then dy dx equals cosine of x. Like in way, actually, I sort of skipped that step and I apologize. And you could put that in like right now, I'm assuming that if we have sine, the derivative of it is straight up cosine, i.e. no negative sign, no negative SIGN now, right? I probably should put that in. I'm just not going to crowd the B. But anyway, I think you get what I'm saying. So now we get d2x dt squared equals negative a omega squared cosine omega t. And please notice again, see, that's that omega squared, right? Like we're just trying to see now from kind of a different angle from going backwards. We're trying to see the big deal that I made last Wednesday. Like, why is everything all about omega squared? Omega squared, what's the deal? Omega squared is what comes out of doing the chain rule twice. It's what comes out of the fact that we're dealing with second derivatives here. And is second derivative like an arbitrary example on my part? Like, is it next week going to be third derivatives and the week after that going to be fourth derivatives? No. We're very, very obsessed with second derivatives here. We very much care about this second order differential equation d2x dt squared equals negative omega squared x because this is all about Hooke's law. This is all just about the mathematical dissection of Hooke's law, which is a statement of a certain force. And according to Newton, F net equals ma. Like this is all about second derivatives because acceleration is a second derivative and acceleration is what gets produced by forces. Like it's not a, so anyway, when we do this, so this is where really are concerned about second derivatives here. And the second derivative brings out that omega twice. So omega squared is what keeps popping up in the differential equation for harmonic oscillation. That's what this is all about. That's what it's about physically. But right now I'm just looking at the raw math. All right. So the second derivative is there. It's negative a omega squared cosine omega t. That's the answer circled. Step 5 for question 2. I'm going to start speeding. I know we only have 20 minutes left. I'm at least going to get to Maisha's question now, I think, I hope. Right. So on the next page now. So now we get, this is Maisha's original question. So B, right? And please stop me if, for whatever reason. B, it says, is x equals a cosine omega t a solution to d2x dt squared equals negative omega squared x? Why or why not? Okay, so that's the question. Now, again, there's a whole background of physical reasons why I'm asking that question. The background of physical reasons is like the last 6 weeks of class, or certainly the last 2 weeks of class. Like, physically, I care about that differential equation that's written in the page. Like that differential equation, d2x dt squared equals negative omega squared x. That is a fancy mathematical way of writing Hooke's law, of writing the second order differential equation that governs or dictates or defines or whatever simple harmonic oscillation. That's physically why I care about that differential equation. Is anything that is described by that differential equation is a simple harmonic oscillator. That's physically why I care about this. Like that's why you're dealing with this in a physics class. Mathematically, though, right now, mathematically, it's just asking, like it doesn't care or even know about the physics. It's just mathematically saying, say we consider this differential equation that we just wrote down, this differential equation, d2x dt squared equals negative omega squared x. Say we just have that differential equation. Now, please note, now again, this is where the Maisha question comes in. That's a differential equation. As far as math is concerned, that is a differential equation. Why I called it differential equation is that it's relating some kind of derivative, in this case, the second derivative. It's relating a derivative of x with respect to t to x. Please note that like the omega is a constant, but x and t are variables. And notice from, well, I'm going to write this down. This is, no, that doesn't, sorry. Okay, notice that, so that's just a raw differential equation that's just been written down, okay? But just from the way it's written, like, again, if I knew nothing about cosines or and this is a really serious point. This is not just to Maisha, like this is to everybody, because this is new math and physics to all of us. I'm saying, and we're trying to unpack the math that we need for the physics. I'm saying, oh, excuse me for a second. Sorry. 1 second. I'm so sorry. Sorry. I'm saying, even if you didn't know about question A or x equals a cosine, anything, like just fresh, someone just walks up to you from the street and says d2x dt squared equals negative omega squared x, just from the way that's structured, you can tell that t is being treated as an independent variable and x is a dependent variable. I say you can tell because t is in the denominator of the derivative expression. That's funny, right? T is in the denominator of the derivative expression and x is in the numerator. That, in other words, x is being treated like the rise in some graph and t is being treated like the run of some graph. So t is the independent variable, x is the dependent variable. The left side is saying, that's funny. The left side is saying the rate of change of x with respect to t equals some function of x. That's what makes this like confusing and weird and interesting and exotic. That's what makes it a differential equation, that the derivative with respect to t is being related to x, not to t. It's saying that the rate of change depends on not the thing that we would expect it to depend on, but depends on the dependent variable called x. Okay, that's the differential equation. Our job, if we just saw that on John's prank show, if we just saw that differential equation, and omega is not part of the difference. It's not in the numerator nor the denominator. Omega then is just some number. It's just some constant. Therefore, omega squared is just some constant. Like I can tell all of that, and I need to know all that just by looking at the structure of the way this thing is written down. X is a dependent variable, t is an independent variable, and omega squared is some constant. Now, my job, when I look at a differential equation like that, my job is to find a solution. This goes to the Maisha question. I want to solve that thing. It looks solved maybe to many of us because it looks like it's already an equation. And maybe it even looks like, well, it already figured out the derivatives. So isn't it solved? Like it took the derivatives. It said they're equal to omega squared equal to times x. I'm saying that to solve that thing, we don't want to take derivatives. We want to find an x. We want to find x as a function of t such that when we want to find some x for which it is the case that when we take two derivatives of it with respect to time, then we get negative omega squared times itself. We want an x as a function of t such that when we differentiate it twice with respect to t, we get back itself x times whatever omega squared is, that constant, times a negative sign. So a solution to this differential equation would be some expression, x equals blah, 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 t, that works, that actually, if we differentiate it twice, would get us that. So apparently, so it's now asking the x that we've just been playing with. We've just been playing with this random x equals a cosine omega t. We've been playing with, we've been taking two derivatives. We took two derivatives, and now the question is being posed, hey, now that you've taken two time derivatives of that x, do you get back something that fits this do you get this differential equation? Does that x satisfy or solve this differential equation once you differentiate it twice? And the answer is yes. The answer is yes, because when we took it, and I think, by the way, I think Maisha knew this. I'm not saying she didn't. I'm just like dissecting the language. When we took two, so I'm now looking at the bottom of the page. I wrote like yes in red, since d2x dt squared, like the second derivative of x with respect to t equals negative omega squared times a cosine omega t. Like I did take the liberty of like, sorry, on the former page. On this page, we got that d2x dt squared equals negative a times omega squared. Remember, those are just numbers. Those are just constants. So it's negative times a times omega squared times the whole expression cosine omega t. Well, I took the liberty to decide that multiplication is commutative. So I just swapped the place of the a and the omega squared because I can, because multiplication is commutative, but I did it for a reason, because I want to, because if I now write it the way on the next page, if I write negative omega squared a, and then I put brackets around the a cosine omega t, because I can do that, because multiplication is also associative, if you know what I'm saying. Like I could do the multiplication in any order I want. So if I put parentheses around a cosine omega t, I realize, oh, land ho, gadzooks, eureka, that a cosine omega t, that whole thing is what I was calling x. So apparently d2x dt squared does equal negative omega squared times the original x. Apparently, if we make x equal to a cosine omega t, it does satisfy, it does meet, it does fit, it does solve our original differential equation. So we say yes. So I don't know if hopefully maybe Manisha will tell me that answers her question, but that's what the question is. So, and why do we care about all of this? Because what we're really saying in English or in physical terms is the differential equation itself is really Hooke's law, really. And the differential equation, Hooke's law, is what we're saying is the condition for any simple harmonic oscillator. Anything any system that's constantly being restored back to equilibrium by a force that is directly proportional to its displacement from equilibrium, any system that is constantly being restored by a linear force will oscillate harmonically. And the solution to that, the way to predict where it is at any given moment in time, is x equals a cosine omega t, or that's one way of writing it anyway. We're saying the differential equation describes the state, it describes the situation of a simple harmonic oscillator. And x equals a cosine omega t, the solution is the equation of motion for a simple harmonic oscillator. Like the differential equation is the condition for simple harmonic oscillation, and the cosine thing is the equation of motion. It is the prediction, the rule for how to know where the thing will be at any given moment in time. The differential equation didn't tell us that explicitly. It contained that information, but it didn't tell us that. So the equation of motion is a solution to the differential equation. I mean, that's the best way I could say it for right now. And I know we have 8 minutes. I'm going to keep going. Pardon me for 1 second, but I'm going to go to the next page. Okay, so then I'm going to next. I'm going to try to speed up a little bit here. Pardon me. Sorry. Okay, sorry. Okay, so next page. I'm going to try to say this quickly. So the next page. Okay, I'm going to say this a little bit, maybe quickly, but now in C, again, we're just trying to practice the math that is underlying the physics here. But now in part C, one way of practicing this idea, again, Maisha's question, like, what does it mean to be a solution to a differential equation? One way we're going to see this now clearly in C, to cut to the chase, is C is going to give us a counterexample. C is going to give us an example of something that sort of looks like it could be a solution. It's going to give us something that has the general shape, the general form or structure of a solution, but the details aren't good enough, right? So in question C, and again, now I'm just like writing answers, like now I'm skipping this steps and I'm just giving you the answers. You and your homework would still do everything in detail, please. But I'm now trying to, make some tracks here. So in C, the question is X, sorry. I'm going to look at the chat. This looks like a good question in the chat. Okay, that's a great question. And okay, so Elizabeth with an S should totally submit this question for participation points. She says, can we say that it is not a solution because -3 is not squared? Great. Okay, on the one hand, great insight. This thing was definitely doomed to not work because we didn't in any way square that 3. That's a good point. And that's really important, good insight. But also, it's also worse than that. It's also because not only didn't we square the 3, but also it was a 3, whereas it should have been a 5. Like, I don't know if this, so when so I agree with her, but I'm also, there's another thing as well. Like, even if we had, in other words, let me put it this way. What I'm saying is, they're asking, is x equals a cosine 5t a solution to d2 dx dt squared equals -3x? what I'm really trying to say here, and this is consistent with what Elizabeth with an S is saying, but I'm also saying something in addition. Wait, hold on. Wait, okay. That's a great question of John's, and you guys can, but do me a favor, hold the chat for a second, just because I know we're running out of time and I want to answer this. But I mean, it's totally a fair question what John's asking everybody else, and I assume they should answer, but maybe answer in the what do you have? What the Discord or whatever you. I mean, I'm psyched if you guys want to help each other after class, please do. Let me, because I only have 4 minutes, let me try to address these questions right here. I'm saying if we try the proposed solution x equals a cosine 5t, okay, that is a harmonic oscillator. I'm totally trying to respond to this question and to Elizabeth's question in particular. X equals a cosine 5t is a solution to something. It is a harmonic oscillator. But if we differentiate that twice, the 5 does get squared, as Elizabeth is saying, but it gets squared and comes out and becomes a 25. So what we would in the end have is d2x dt squared equals negative 25t. What was proposed was d2x dt squared equals negative 3. I'm sorry, I said t, I meant x. Wait, okay. Awesome, thank you for that, John. But what I'm trying to say is, it's not that the 3 did have to be squared, but more than that, the number, this would have worked. What I'm really saying is the reason that this doesn't work is that not only that 3 is not the same thing as 3 squared, but that 3 is not the same thing as 25. What I'm really saying here is we could have written d2x dt squared equals negative 3x. That totally could be, that is some harmonic oscillator. But the solution to that would be x equals a cosine of square root of 3t. Like, I'm not saying that, in other words, what I'm really want to make clear to everybody, I'm not saying the number next to the x has to be a perfect square. It could be any number we want, but whatever number it is, the square root of that number will be the omega in the cosine expression. That's why we call that number, in other words, in this case, 3, in the case that's given right here, 3 is equal to omega squared. I know 3 is not a perfect square. That's okay. Like, the square root of 3 would be omega here. But the problem is that the proposal we were given, 5 was treated as omega. What I'm literally saying here, and it says it in completely illegible red handwriting next to, what I'm really saying is that differential equation is a harmonic oscillator. And that equation of motion, that cosine, is also a harmonic oscillator, but they're not the same harmonic oscillator. What we have here is 2 different oscillators. We have oscillators that might have the same amplitude. They both might be started at the same place, but they're going at different cycling rates. One of these oscillators is going back and forth, back and forth, back and forth at 5 radians per second. And the other one is going a lot slower. It's going back and forth at the square root of 3 radians per second. It's okay that 3 is not a perfect square. We could have made it 9 and it would be easier for us to picture, but it still wouldn't be the same oscillator as one whose omega is 5. I'm saying these are both oscillators, but of 2 different angular frequencies. One of these is 5 angular frequency, the other is a 3. Or put another way, for one of them, omega squared is 25, and the other one is 3. They're both harmonic oscillators, but they're not the same one. So this cosine expression is not a solution to that differential equation. I will say this. There actually are, as you might notice, there are 4 more pages of notes. I'm going to upload the 4 more pages of notes. I would like you to look at them. Like, I don't want to fall. So there was a couple things I did because I was, for whatever reason, I didn't. These notes here, it goes all the way through F. F relates us back to what we were talking about last Wednesday about phi, the phase constant. F gets us back to that. And then the last 2 pages of notes try to tie together part F with what we were saying last Wednesday. I'm going to spare you right now because, I mean, class is over. I have to go. You have to go. Now, remember that we have to, like, review this next time. But please do note that these last bits are in the notes. We're going to end now. I have another class that comes in very fast. So thank you all. So sorry, I'm a little scared. No, it's okay. Thank you for saying so. Thank you for saying so. And you can put that in the chat. No, but I just got twitchy at the end because I know class is ending. But thank you for saying so. No problem at all. And thank you for making the Discord with people. And I think that's like really important. I am going to end now. And I can't really stay to answer any questions. I apologize because I've got a class that comes in early after this, just for this week. So I'm going to go. But thank you all very much. Thank you. Awesome. I'm going to stop the recording. Okay. So bye.